Hello everyone, let's continue with our course, and today what we're going to study is Hesss Law. So let's go and jump to our app. Perfect. So what we're going to study today is Hesss Law, okay? And this is very important because it's intrinsically related to what? To something that we have already studied, which are heat of reaction. But most importantly, now we're going to talk about heat of formation. And you may ask, formation of what? Well, specifically about the formation of a product. So what we're going to talk about is the special type of change of H, which is called of product. Very well, the formation of a product. So basically, HF, what is going to tell us is how much energy, right, you need to create the bonds, chemical bonds of a product. Very well. So we're not talking only HF, right? It's the change of HF. Very well. Now let's go and set some standards, right? Or some specifically references. And let's talk about the elements. Like, for example, carbon, its elemental state, which is a solid. Or, for example, oxygen, right, which in the elemental state is a gas, or nitrogen also, for example, in which the elemental state is also a gas. Well, in all of these cases, right, always, the change of F is going to be 0. Why? Because they are elements. They are already being formed, okay? This is why we're going to set as a reference, and to make things easier, that whenever you're talking about elements, the change of H is always going to be 0. And that's going to be the rule. So let's stick to it so we don't mess things around. So let's continue. Now let's go immediately to something practical, to a practical example, right? And let's remember our combustion reactions. So if I have, for example, carbon in the form of a solid, and I add oxygen, elemental oxygen in the form of a gas, right? And I do use this stoichiometry for the reaction. What I am going to get is CO2. So nothing new, nothing that we know. And I also know that the enthalpy, right, of this reaction, the regular enthalpy of this reaction, if I do it at 298 Kelvin, right, I am going to release to the environment minus 393.5 kilojoules. So since it's a combustion, right, it's also a very exothermic reaction. It's very powerful, right? It's going to release a lot of energy, right, just because we're talking about what? A combustion. And now, since we are going to make the approach of what? Of the products, I can also say, if I'm going to use this also as a product, that the enthalpy, right, of formation, if I'm going to use this perspective, is also going to be the same as what? As the enthalpy of combustion, which in this case is also going to be minus 393.5 kilojoules. Okay, so there's a similarity between the standard enthalpy and the standard enthalpy of formation, if what I am looking for actually is what? The product, right? In the sense of a product. I think this one's better. Okay, very well. So give me a second. Excellent. So let's continue. Now I can set my reaction like this, right? Carbon, solid, plus oxygen, gas, that is going to give me CO2, that is also going to be a gas. And I know that it's going to release, right, the formation of this compound is going to release minus 393.5 kilojoules. Very well. But guess what? Technically speaking, there is nothing that will not allow me to do this. That I can transform what? CO2 into carbon that is solid, and oxygen, that it's a gas, right? Because a chemical reaction can go through this direction, or it can go in the opposite direction. And actually, there is absolutely nothing that forbids me to do that. And what about the enthalpy of formation here? Well, in this case, we would be talking about the enthalpy of formation not of one compound, but of two compounds, which would be the enthalpy of formation of carbon solid, right, plus oxygen. Oh, I'm missing a 2 here. Thank you. Oxygen in the form of a gas, right? Give me a second so I can erase this correctly. O2 in the form of a gas. Perfect. And since what I am doing here is that I am changing, right, the direction of the reaction, right? If I was having here what? The release of energy, here I'm going to have to do what? To add energy to what? To the system. To which system? This system. So this system was releasing energy, that's why it's negative, and this system requires to add energy so we can get this product. So in this case, I'm going to have plus 343.5 kilojoules. Okay? Why? Because I changed the direction, and there's nothing wrong with that. There's nothing that will not allow me to do it. So once we said that, let's go and ask Dalton what does his law has to do, have to say about this. So for example, if I have 1 mole of carbon that is solid, and I add 1 mole of oxygen that it's a gas, and I know that this is going to be transformed into what? Into 1 mole of CO2, right? That is also going to be a gas. I know that it's going to release, right, certain amount of energy, which is minus 393.5 kilojoules. Okay, but since the law of multiple proportion of Dalton actually says a lot of things in terms of chemistry, right? I can do something that it's kind of obvious at the beginning, and if I multiply this by 2, that is that I also need to multiply this by 2, and if I am using what? Twice the amount of fuel and twice the amount of oxidizer, it's logical that I also going to have the twice of energy release. And that's important, right? Because this is the way in which we will solve problems according to Hesss Law. So if that is true, and I burn 2 moles of carbon, that it's a solid, plus 2 moles of oxygen, that it's a gas, what I am going to get are 2 moles of CO2, so nothing new, that it's a gas from that perspective. And the amount of energy of formation that I'm going to get for what? For 2 moles, right, is going to be minus 787 kilojoules. Very well. Now, it's something important to say that usually when we're talking about the term formation, we will not talk about numbers different than 1, right, in the coefficient of whom? Of the product. So every time that we talk about a formation, we always need to refer everything to a 1 in the coefficient, the stoichiometric coefficient for the products, because remember, everything has to do here with products. Very well. So in that sense, let's take another example. And if you have, for example, half of a mole of nitrogen, that is what? A gas, plus 1 mole of oxygen, that is what? A gas, right? I am going to get 1 mole of NO2. Very well. And the enthalpy of formation is going to be, for this case, plus 33.2 kilojoules, I think. Right? I don't remember if it's joules or kilojoules. I'm mostly sure that it's kilojoules. Meaning that since this is positive, right, it is an endothermic reaction. Very well. That means that I need to apply energy to the system. To which system? To this system. And I can talk about what? A formation, because here the coefficient is 1. So yes, excellent. Everything check. This is good. Perfect. We can talk about the enthalpy of formation for this reaction because everything has been set and referred to a 1 here. But sometimes you will find examples in which that is not the case. A very simple case. So I'm going to have 3 moles of oxygen. That is what? A gas. And it's going to be transformed into 2 moles of another gas, which is ozone. Okay? This happens in the atmosphere all the time because there are UV light that interacts with oxygen, and then it will transform into ozone. Okay? And the enthalpy of reaction, right, for this transformation is going to be plus 286 kilojoules. So we need to apply energy, right, to the system, which makes sense. But we cannot talk about what? The enthalpy of formation. Why? Because this is not A1. We need to transform that into a 1, sorry, if we want to talk about enthalpies of formation. So Dalton again comes to the rescue because of the multiple proportionality state that he proved to be truth. We can do this. So if I have 3 moles of oxygen, that is what? A gas, and I want to transform this into 2 moles of ozone, which is also a gas, and I need to transform this coefficient into a 1, well, pretty simple. I only need to divide this by 2 and divide this by 2. But that also means that the enthalpy of the reaction, which is 286 kilojoules, right, also needs to be divided by 2. So in this case, the enthalpy of the reaction over 2 is the same as the enthalpy of formation, which would be 286 kilojoules over 2, and this will give you 143 kilojoules for what? For 3/2 of oxygen that will be transformed into 1 mole of O3. Okay, and both are gases. Very well. Questions up to here? I hope not. If not, you can always appoint to me office hours. So please go and work with the example. 5.12 from the OpenStax. Right? I like to use this book for this topic because I think it's very well explained, but just check on the chunk if you have any sorts of doubts too. Very well. So today is going to be a little bit longer, the video, because I want to explain further things. So I hope that we will not get any problems here. Very well. So let's get into something a little bit more complicated. And imagine that you have carbon in form of a solid, and you want to add oxygen in terms of what? Of a gas. This is another combustion reaction that we already know, right? Which is CO2, and this is also going to be a gas. And we already said that the enthalpy of formation for this reaction is going to be minus 394 kilojoules. So no news. Everything goes well here. And this would be the path that I would follow if I add what? A whole mole of oxygen. But I can do something different. I can get creative and say that now I'm going to do the reaction with 2 different steps. So I can have, for example, carbon that it's a solid. And instead of adding 1 mole, what I will do is that I will add half of a mole, right, of oxygen, which is a gas. And what I will get is what? CO. And I can measure that energy of formation. And for this reaction, the enthalpy of formation, right, is going to be minus 111 kilojoules over mole, okay? And after that, I can take now this product and add what? Another half of mole of oxygen, all of them gases. And then what I am going to do is that I'm going to transform CO into CO2, and I can also measure the change of energy for that reaction, and it's also going to be exothermic, and it's going to be minus 283 kilojoules. Very well. So if you can see, right here, what I am reaching is CO2, and what I am reaching here is also CO2. The only difference is that I use 2 reactions instead of only one to reach exactly this product, okay? And if I am doing the reaction in 2 different steps, right, that means that the total energy must remain the same no matter what, because I am just splitting the reaction. That means that the addition of these 2 energies should go and give me, right, the whole of the initial reaction, which in this case would be this number. So let's go and perform the addition of also these 2 reactions. Very well. So let's see. I have C, that is carbon that is solid, plus 1/2 of an oxygen that is a gas, and that is going to give me CO. And the enthalpy of formation for this reaction is going to be minus 111 kilojoules. Perfect. Now the second stage of the reaction is that I'm going to use CO2, that is what? A gas, right? Plus another half of what? Of oxygen, which is what? A gas, and that is going to give me CO2, also in the gas phase. And the change of enthalpy for formation of this reaction is going to be minus 283 kilojoules. Very well. So what I literally am going to do is that I'm going to add everything here, right? Let's change color to gray. Okay, and what I'm going to have, well, I need to add everything that is on the left of the arrows and everything that is on the right of the arrows. Very well. So I have my arrow, and I'm going to add everything. So I have C, that is a solid, plus 1/2 and 1/2, 2/2 of oxygen, that is a gas, plus CO2, that is what? A gas, right? And on the other side, I'm going to have CO, which is a gas, plus CO2, which is also a gas. And if I add these numbers, right, then the enthalpy of formation is going to be 3 plus 1, 4, 8 plus 1, 9, 2 plus 1, 3, and both negative. So it matches, right? It matches the amount of energy that we have at the beginning of the reaction, this number. Very well. But what about the chemical reaction? Do we have the same? Yes, we do, because exactly in the same way, right, that I have, sorry, this is a 2, this is CO. I have CO on the right side, I have CO on the left side, right, and I can transform this chemical reaction into carbon, that it's a solid, plus 2/2, which is 1 mole of oxygen, that is going to give me CO2, that it's a gas. And since it's a 1, I can just erase it, right? And then I get, at the end, the same reaction that I start from the beginning. Okay, so I'm going to leave up to here because the video is really long right now and I don't know if I'm going to have troubles uploading it. So I'll give you some hints on how to solve reactions with problems with Hesss Law in the next video. See you.